Reminder, SQ2 due tomorrow. As usual, I'll have the name sheets here with the various discussion instructors' names written thereupon. And I've added a question to SQ3, recited on this weekend. And get some more points. And I have a feeling everybody can respond to this question. Perhaps some of you have seen it. If you've not seen it, download the new version of SQ3 and submit that rather than the original version. That's due this Thursday. Let's now proceed with electrochemistry and with good fortune get this stuff wrapped up and plow into chapter 23, which will be our last chapter. We'll not have time for chapter 24, I'm sorry to say. Nernst equation, the second aspect of electrochemical arithmetic. Very important aspect. Nernst equation is derived from fundamental thermodynamic considerations. This is shown in the notes. It all comes from delta G equals delta H minus T delta S, and delta G 0 equals delta H 0 minus T delta S 0. Now, I don't care about your being responsible for the derivation. You may have noticed this is on the information sheet. Your job is simply to be able to use it successfully. So let's take a look at some examples which put to use this very important statement. Why important? Why useful? Well, for example, this equation forms the basis of operation of a pH meter. If you've done your part of the job and read the information leading up to this that's in the notes, you already know this. Calculation of a whole slew of equilibrium constants. Very important thermodynamic information. Most of which are determined by electrochemical measurement and application of this equation. And where does M come from? As in Faraday's law considerations. N is moles of electrons transferred. And the only way you can know what N is to write the correct net cell reaction. Because that tells you what N is and nothing else. Example, first we retreat to this reaction which we've already looked at. The standard electrochemical potential is plus 1.10 volts, which again we've already determined. That, of course, this 0.76 volts corresponds to the zero that you see in table 2 for the aqueous system oxidation of zinc metal in the presence of water to the hydrated zinc ion, associated with the loss of 2 moles of electricity per mole of hydrated zinc ion produced. The plus 0.34 volts comes from the half reaction, which shows the oxidation of copper in water solution to hydrated copper ion, and liberating 2 moles of electrons. But in coupling these half reaction systems, the copper-copper ion half reaction system is the half reaction of lower E0. So that's the one that gets reversed. And on reversing it, we change the sign on E0. So it becomes, instead of minus 0.34 volts, which corresponds to the fact that copper is quite a weak reducer, much weaker than zinc. So now we're turning that around to look at the effectiveness of hydrated copper ion behaving as an oxidizer, and in so doing getting reduced to copper metal as the water molecules go into the aqueous solution. For the reaction as is tabulated in table 2, minus 0.34 volts, reversing plus 0.34 volts. So E0 cell is plus 1.10 volts. Here's the Nernst equation. I've written in all the parts except N. What's N? There's the reaction. What's N? Directive, if you've not yet realized this. You can determine N on examining the net cell reaction by looking at moles of stuff oxidized with respect to oxidation product, how many moles of electrons must be lost, or moles of stuff reduced? You get the same answer. It has to be. Otherwise the system wouldn't be electrically neutral. Moles of stuff reduced. How many electrons must be consumed to produce moles of reduction product? Well, zinc is being oxidized from zero oxidation state to this complex metal ion of zinc in the +2 oxidation state. Copper ion in the +2 oxidation state is being reduced to copper metal. So N is 2. That's all. 2 moles of electrons are lost as a mole of this becomes oxidized to this. And what are those 2 moles of electrons consumed by? The 1 mole of this as it's reduced to 1 mole of this. Enough said. Now a peek at how the Nernst equation works. What control do we have on this system besides changing temperature? We're not going to consider temperature changes. Well, these puzzle parts are all constant. So the only control we have is adjustment of concentrations for the species which are components, solution components of the net cell reaction. So we can change this molarity, we can change this molarity. How should we change these molarities? If we wish to make E cell increase. If we want E cell to be bigger than E0 cell. Now you have to understand some arithmetic to answer this question. And pay attention to this minus sign. Because if the molarity of zinc ion up top is smaller than the molarity of copper ion down below, then you have the log of a number which is smaller than 1. What is the sign on any number? Log smaller than 1. Negative. So you get a negative times a negative. And that should follow eminently or obviously from examination of the reaction equation. If you want to provide more thermodynamic drive for any reaction to go left to right as written, you up the molarities of the reactants while lowering the molarities of the products. Because if you lower the molarity of the reactants and up the molarity of the products, you're going to drive the thing this way. Well, you want to drive it that way. Because this way is the way in which the system operates spontaneously. Simply put then, for this system, lower this, increase this. The lower this is, the higher this is, the higher is E cell. So, the concentrations which I've asked you to consider, question 21, is zinc ion at an initial molarity of 0.100 molar and copper ion at an initial molarity of 2 molar. You put in the numbers, you can do the arithmetic. E cell is plus 1.17 volts. Because all you're doing to solve this puzzle is taking the log of 0.010 divided by 2. So you got the log of 0.005. Right? Times 2. That's a negative number, but negative times a negative gives you a positive. So what you got here adds to this and makes E cell bigger than E0 cell. Now, we've already talked earlier about how this cell can be acted on by treatment with ammonia to make both E0 cell, previously we talked about how to treat this system with ammonia to make E0 cell go up. Now we can do the same thing with E cell by treatment with ammonia. You can make E0 cell go up as well as E cell. Remember what we did? We looked at table 2 and we recognized that this is a collection of thermodynamic stability information. Right? And in so doing we realized that the copper ammonia complex ion is a good deal more stable than the copper water complex ion. And the zinc ammonia complex ion is a good deal more stable than the zinc water complex ion. But zinc is behaving as the stuff that's the reducer, the stuff that's getting oxidized. So you want to up the favorability of converting the reducer to the reduction, to the oxidation product, pardon me. You want to up the ability of zinc to behave as a reducer. So you put ammonia in the zinc ion half cell. That's the anode half cell. The half cell in which oxidation occurs. You also put ammonia in the copper ion half cell? Hell no, because that would convert copper water complex ion to copper ammonia complex ion, and that's a more difficult to reduce species than the copper water complex ion. Because the copper ammonia complex ion is more stable than the copper water complex ion. You don't want that. Another question. I mean, this is a physical gadget, this electrochemical cell. And for the cell as we described it earlier on when we used this as an illustration of how to couple and make an electrochemical cell, picture for which is on page 22.8. We already looked at that stuff. For this system, zinc is the anode, copper is the cathode. Can I take this system and take out the copper cathode and replace it with a silver strip as a new cathode material? Well, of course, I can do anything I want. You know, I can go in there and I can put bananas in the cell. Who cares? I'm not going to do that, but I can, right? You got to be careful about this word can and can't. From my observations during life, I find the word can't to be the most commonly misused word by speakers in the English language. Can't. Because what they usually mean is won't. I won't do it. You know, will you give me a break? I can't. Baloney. That means you won't. You don't want to do it. Tell me the truth, damn it. Don't lie to me. Don't say can't. Because can't means impossible. That's what it means. And if you're my boss and I ask for a raise and you say can't, you're lying to me. What you mean is won't or don't want to. That's what you mean. So at least have the guts to tell me that. Don't cop out with can't. I mean, think about it. I'm sure you've heard this many times. It's funny people hardly misuse can. But they misuse can't all over the place. Cop out for won't or don't want to. Okay? So, we got this cell set up. I'm not going to draw the picture again. If you want to see the picture, go back to page 22.8. I will physically grab the copper cathode, remove it from the system, replace it with a silver bar to serve the purpose of being as the cathode, and connect the wire to the silver bar and take the silver bar and stick it into the solution that contains the copper ion. Will this system still operate? Will it still operate with the same electrochemical potential? So I've asked two questions. Number one, will the system still operate? If you don't know this, silver is the number one best conductor among metals. But we generally don't have our homes wired with silver. Because we don't want people breaking into the home to steal the electric wires from the place. Because silver is dang gone expensive on a per gram or per mole basis. Okay? So we usually have our homes wired with copper. Some homes have been wired with aluminum. Not good. Aluminum is a hell of a lot cheaper. But aluminum is pretty easily oxidized to aluminum oxide, and you don't want that. In any case, if I take out the copper strip and replace it with a silver strip, now serving the purpose as behaving as the cathode in this system, will the system still function?
Yes.
Will the system function with the same electrochemical potential? Well, half of you, response to the first question, from what people I heard, correct. Response to the second question, from what people I heard, wrong. Why is it wrong? Why is it perfectly legitimate to take this system, replace this copper strip with the silver strip serving the purpose of cathode, and I changed nothing operationally. Number one, how does the strength of silver compare to copper as a reducer? We've told you that silver is an excellent conductor because I think you recognize that an anode or a cathode has got to be a conductor. An electrical conductor. How does silver compare to copper as a reducer? We've talked about this before. Let's put it to use. Or look at the table. Which is the more readily oxidized metal, silver or copper? Look at the table. Copper. So silver is a poorer reducer than copper. So if I put the silver bar in the copper ion system, is the silver bar going to reduce the copper ion? Heck no. Is the silver bar a good conductor? Absolutely. So the only thing that's going to happen differently is that as copper ions get reduced to copper metal, the copper atoms will now be depositing on the surface of silver. So if I want to electrodeposit copper on silver, this is the way I do it. But if I want to keep on building up a quantity of pure copper, then I'm not going to make this change. But operationally, I change nothing if I take out the copper bar and replace it with a silver bar. I don't change E0, I don't short circuit, I don't do anything wrong, and I'm using an excellent conductor. Well, I can also go over to the anode system, pull out the zinc bar, and put in a silver bar. What happens now? System still function? Yes or no? Does the system still function? If I take out the zinc bar, the anode, and replace it with a silver bar, intending it to be the anode, will the system still function? What's getting oxidized in this system? A material which is a good conductor, because it's a metal, that's zinc, and which is a stronger reducer than copper. That's why it's capable of reducing hydrated copper ion, right? So what's going to happen if I take out the zinc bar and put in a silver bar? The silver bar is certainly an excellent current carrier. Is the silver bar going to cause electrons to flow from itself into the copper ion as silver gets oxidized to silver ion? Absolutely not. Silver can't reduce copper ion. We just discussed that. So if I make this physical change, E cell and E0 cell will become what? Zero, nothing. No more reaction. All right, we proceed. Take a look at table 2. Follow the directive up here. Again, if you've done your work, you've read pages 22, 22, and 22, 23, recognizing that on page 22, 23, there's a discussion of how pH can be measured electrochemically. I suppose pH could also be measured with a rigorously constructed conductivity gadget. And an electrochemical cell is a conductivity gadget. But I'm talking about a conductivity gadget whose operation does not depend on redox. But I really haven't researched it, I don't know. So in any case, at page 22, 23, you see a discussion of how electrochemically a pH meter can be constructed. The pH meter that's described on page 22, 23 is composed of the two half cells, zinc being oxidized to hydrated zinc ion. That's what we got up. That's the half cell corresponding to oxidation for this net cell reaction. And the standard hydrogen electrode. Now the standard hydrogen electrode, as it's written in the table, table 2, this hydrogen in the presence of water being oxidized to hydronium ion. So that's the one that's going to be reversed if that half cell is coupled with the zinc ion half cell. because the zinc going to zinc ion is a more favorable electrochemical potential half reaction than the oxidation of hydrogen to hydronium ion in the presence of water. So it'll be hydronium ion that gets reduced to water as well as hydrogen. I mean, gets reduced to hydrogen plus water. Okay? So I ask again that you look at the half reaction list, table 2, and see if you see a number of different half reaction systems which could be used as components of a pH meter. What requirements must be met if a half reaction system, a half cell, is to be used as a functioning component of a pH meter? What? Let this information in this table talk to you. What? What must be a component of the half reaction system if I want to measure pH? Hydronium ion? You betcha. You see other half reactions that have hydronium ion in them? What else? Hydroxide ion. Hey, either one. I can use either one. But the standard hydrogen electrode is the most obvious. At least, I don't know about most obvious, but I'd say it's the simplest. And arithmetically, it's certainly the simplest to deal with because it is our defined zero electrochemical potential standard half cell reference point. Question as we proceed. We're going to consider zinc reducing copper sulfide to become zinc sulfide and copper. Look at table 2. Look at table 2 to recognize that this reaction as written is or is not spontaneous. Look at table 2. If you don't have your notes with you, you're not following directives. Is this net redox reaction as written a spontaneous transformation, yes or no? Yes or no? All right, let's consider it an acidic solution. Okay? Look at table 2. Because I guarantee when you deal with the last exam, you have to know how to interpret and use the information from table 2. So that's why I'm prepping you for this. I want you to be successful. If zinc is oxidized to zinc sulfide in strongly acidic solution, what's the E0 value? Zinc becoming zinc sulfide in strongly acidic solution. That means hydronium ions hanging around someplace. What's the E0 value? 1.405. Okay. If zinc is being oxidized to zinc sulfide in strongly basic solution, what's the E0 value? What is it? 1.12. You're not looking at the right data point. Maybe I better look at this information as well. Because what I'm asking now is that you provide the interpretation. So I better see to it that you provide the correct interpretation. Not for my benefit, for your benefit. Who said 1.405? More than one person. I asked for zinc being oxidized to zinc sulfide under what conditions? Strongly acidic. And I'm looking at 11. That's zinc in the presence of HS minus and hydroxide ion. Is that strongly acidic? Come on now. You got to pay attention to the system chemistry. You can never avoid PSI. If you avoid PSI, the game is lost. Game over. Kaput. You will lose. We don't want that. So I suggest strongly for my first question, zinc being oxidized to zinc sulfide, under strongly acidic conditions, you look for a different half reaction. .04 corresponds to zinc being oxidized to ammonia complex. I want zinc going to zinc sulfide. Or do you have a problem? What is the problem? It's not in the table, is it? So I have a question. Relative to 1.405 volts, that's the oxidation of zinc to zinc sulfide under strongly basic conditions, right? Because that's a standard electrochemical potential, which means the hydroxide ion molarity in that system is 1. Right? pH 14. If I put in this table zinc going to zinc sulfide in strongly acidic solution, how will E0 compare to 1.405 volts? Will it be the same as, bigger, or smaller than 1.405 volts?
Smaller.
Smaller, why? And you can't tell why, then you don't understand. But I want you to understand. That's why I play these games. Why smaller? You betcha smaller. Guaranteed smaller. Why? You're trying to form a sulfide, aren't you?
Zinc sulfide dissolves in acidic solution.
What is that?
Because zinc sulfide dissolves in acidic solution.
In what? You think so? You did this work. Are you in the lab?
Yeah.
You do assignment 6?
Yeah.
Then you ought to know the answer to this question. You found out that zinc sulfide, for example, can be dissolved in 2 molar sulfuric acid solution. But in acetic acid solution, which is acidic, you ain't going to dissolve zinc sulfide. Not very effectively at all. So you got to be careful. When you say acidic, you've not said enough. Because there's a great deal difference in the acidity of 1 molar sulfuric acid solution versus 1 molar acetic acid solution. A huge difference in acidity. We've been through all of this, chapter 18, right? But sulfide is a powerful base. And any powerful base has a natural, powerful tendency to react with any H+ source. So the more acidic the system, the more difficult it is to form zinc sulfide. Okay? Now then, if my memory's right, the data points are in the table. Should I ask the question, how about forming copper sulfide in a strongly acidic or strongly basic solution? What do you say now? Are you looking at the half reactions? Number 19, copper in strongly basic solution becoming copper sulfide plus 0.76 volts. How about number 26? Copper in the presence of H2S producing along with copper sulfide hydronium ions. How about that? And since this is a standard half cell, that means the hydronium ion is 1 molar. Voltage plus 0.13 volts, 3.4 volts. Isn't that a lot smaller than plus 0.76 volts? Screaming at you. It's a lot easier to form copper sulfide in the basic solution than it is in the acidic solution, which we know from chapter 18 stuff. Okay? So to answer this question, zinc becoming zinc sulfide, copper sulfide being reduced to copper in acidic or basic solution, since we don't have the half reaction in there that shows zinc being oxidized to zinc sulfide in the presence of H2S as the sulfide source and hydronium ion as a product, okay, we can't really answer the question. So what we really need to know, is how the stabilities of these two materials compare in strongly acidic solution relative to how the stabilities of these two materials compare in strongly basic solution. That we have in the table. Because in the table we got zinc becoming zinc sulfide in the presence of hydroxide ion and hydrogen sulfide ion, and we got copper becoming copper sulfide in the presence of hydroxide ion and hydrogen sulfide ion, right? Those half reactions are respectively 11 and 19. So we see that in strongly basic solution, this reaction goes. Has a quite substantial E0 value. And if you get the data for zinc becoming zinc sulfide in strongly acidic solution, which shortly I'll show you how to get. How about that? We like to first offer the mystery and then show you how the mystery can be solved. Okay? That's really what science is. The beauty of science is that we're forever facing mysteries. I mean, Mother Nature is really something. The more we learn, the more we will recognize there is to learn. That's what goes on in science. That's beautiful. This endeavor may well wear you out, exasperate you, frighten you, knock you down, make you mad as hell, make you happy as can be. But it'll never bore you. No way. Not this stuff. So I'll ask a question. For you folks who have been in 46L, which is most of you, and have done assignment 6, you found zinc sulfide is dissolvable in 2 molar sulfuric acid solution, didn't you? Was copper sulfide dissolvable in 2 molar sulfuric acid solution? Yes or no?
No.
Yes or no? You did this in lab, and it can't be too far long ago. Copper sulfide dissolvable in 2 molar sulfuric acid solution? Not in the least, practically speaking. Copper sulfide as well as silver sulfide are so horribly stable that I don't care what the molarity is of hydronium ion. You can't get those things to hardly budge with respect to solubility. Sure, they're more soluble in the acidic solution than the basic solution or the neutral solution. But the moles per liter solubility is so tiny that practically speaking you haven't dissolved anything on a per mole basis. So you had to go to assignment 8 and figure out how to get rid of these sulfides by not only strong acid attack, but oxidizer attack. Then you could finally beat up sulfide ion. That's assignment 8, 46L. So I want this stuff to connect, and it makes elegant sense. I've discussed this so many times with my colleagues. They talk nothing about lab in class. So how the hell are these people going to learn? What's going on here? It makes no sense what you're doing. You got to make the connection if you want to get the learning that's really available to you. So, since we've recognized that copper sulfide is considerably more stable than zinc sulfide in acidic solution, right? Copper sulfide still, practically speaking, doesn't dissolve. The zinc sulfide does dissolve. It's a pretty good bet that if I run this reaction in strongly acidic solution, the E0 value will be bigger or smaller than running this reaction in basic solution. Bigger or smaller? Because in basic solution, these sulfides are really stable. And now we got a handle on the E0 value, don't we? That's 11 and 19. How do you think this E0 system will change if I run this in strongly acidic solution? Where I've recognized I'm going to reduce the stability of zinc sulfide considerably, but practically not affect the stability of copper sulfide. So what do you think is going to happen to the E0 value for this thing?
Smaller.
It's going to get smaller. Hey, that's where the understanding lies. All this chemistry we've been talking about all term. We want it to fit together. Then you see the big picture, then you understand. All right. We move to 24. 24 says, let's consider the oxidation of copper to hydrogen sulfide ion in the presence of hydroxide ion to copper sulfide. 1.5 reaction we just talked about, right? Number 19. But we're going to do the oxidation, but we will, for this system, do the oxidation with half reaction 39. Take a look at the table. Take a look at half reaction 39. Because half reaction 39, which is this half reaction reversed relative to the way you see it appearing in the table, okay, shows water with oxygen over the water functioning as an oxidizer to become hydroxide ion at pH 7.00. Right? Isn't that what 39 says in the notes? Oxygen, of course, is the oxidizer. Water is just a medium in which that this oxidation occurs. All right? If I want to operate, if I want to apply Nernst to this, I got to have an E0 value over here. How do I get E0 for 39? Have you looked at the notes that are attached to this table 2? Which have reminded you that there are 4 half reactions in this table which are not standard state half reactions. So the voltages that you see listed for these 4 half reactions are not E0 values. They're E values, but they're not E0 values. And if I want to get E0 for a system, I need to know E0 for each half cell. So I ask again the question, what E0 shall we apply to number 39? And now I'll give you this hint. You have a choice of 2. 39. Look at the table, because that in the main is what this lesson is about. How to use this table. On looking at the table, tell me which E0 values we could apply. Look at the table. Tell me which E0 values we could apply to 39. There are 2 of them. I'm listening. Both of these E0 values will be positive because the half reaction question will have to be reversed in order to complete the coupling process. I'm hearing 0.40 volts and plus 1.23 volts. Anybody support that vote? Anybody support that offering? So you don't like that offering. Well, I like it because it's right. Do you not see that for the 2 half reactions in question, I don't remember the numbers of the half reactions right away. Let me go back and peek. One's 35 and I think the other one's 41. Yeah, well, I did remember them. 35 and 41. See half reactions 35 and 41. Do each of these half reactions, if I write them in reverse, show me oxygen behaving as an oxidizer? Show me oxygen behaving as an oxidizer as a function of pH. One behaving at standard state hydronium ion concentration, and the other behaving at standard state hydroxide ion concentration. That's the pH 14 job, right? Hey, I'm just wanting you to apply the knowledge we have of acid-base chemistry to be able to understand and put to use this stuff. Well, I find this number the easiest to deal with. Oh, what? Only 2 sig figs. Okay? So I am going to use 35. And there's another reason for using 35. It's got nothing really to do with the simpler numerical value 0.40 versus plus 1.23. Why do you think I choose to use 35 instead of 41? What's this? As this system runs, what's happening to system pH? What's happening to system pH? Increasing, isn't it? Isn't this a hydroxide producing system? Well, then I prefer to use the system which has got hydroxide ion in it. That's why. Just chemistry. What else? Okay. Now let's look again at 39. Another note that's attached to the redox table, table 2, is to direct you toward recognizing that certain of these half reactions, in order to be part of an electrochemical system which operates, an electrochemical cell which operates, have to be fitted with an electrode. Let's take a look at the simplest, most obvious case, the standard hydrogen electrode. That's the half cell with the assigned E0 value of 0. Do you see why that has to be outfitted with an electrode? What's an electrode? What is an electrode? You ever see batteries? You ever look at your car battery? Does it have electrodes? Flashlight batteries? Electrodes? What's an electrode? What's an electrode? You think it's a current carrier? Is an electrode a current carrier? You're daggone right it's a current carrier. Is hydrogen gas a good current carrier? Water? Hydronium ion? These all good current carriers? Can you hook these to an external circuit? I'd like to see you try. That'd be fun. A number of years ago in the chemistry department, we observed a student who was attempting to do a synthetic process, and in so doing, the student was instructed to take the condenser and charge it with dry ice. The student went to the ice cube bin, got a collection of ice cubes, brought it back, and was feverishly rubbing these things with paper towels. They won't stay dry. That's not the kind of dry ice we were talking about. Well, these things happen. I hope sooner or later the student learned to laugh at himself or herself, whatever the case may have been. Okay? Oh, what was I trying to do here? Dry ice. Dry it up. Okay. Wonderful. Okay. So, the standard hydrogen electrode is clearly an example of an electrode which has to be fitted with an external electrode. Most commonly used such for that is a strip of platinum. Platinum, marvelous electrode material, because the other condition which an electrode must meet in order to serve the purpose of being a non-interfering part of an electrochemical system is that it must be non-reactive in the system, unless it happens to be the anode metal, which is not only functioning as an electrode, it's also functioning as the REDUCER, okay, the reducer. How about that? Next question. To run this electrochemical system, must I separate the half cells? Or can I put all this in the same pot, like you can do with a car storage battery, where you can have the anode and the cathode? Because in the car battery, lead's the anode, lead dioxide's the cathode. I mean, not the cathode, but the material that is reduced in the cathode compartment, okay? As long as I keep those two, since they're both solid phase, from contact with each other, works fine. I don't have the solution components of the half cells. I don't have to separate them. How about here? Can I put these half cells together and have everything work fine? I mean, copper's the reducer, it's solid state. What's going to happen if I expose copper to oxygen, the oxidizer, while the copper is standing in hydrogen sulfide ion-containing solution and hydroxide ion-containing solution? What's going to happen if I allow the oxygen to intermix with the anode half cell that contains the copper? Will I get a redox reaction? Absolutely. But that's going to be a short circuit, because that copper is going to react with that oxygen, boom, on contact in the same half cell system. I mean, in the same cell system, because they're in contact. So here I got to separate. Okay, now let's get further at this system. If we choose to use 0.40 volts as the standard electrochemical potential for 39, then I will get plus 1.16 volts as the E0 for this system. Minus 0.059 V. Times log Q divided by N. What's N? What's N? Q? Just look at the reaction equation. You know how to do that part. Hydroxide ion molarity to the fourth over hydroxide ion molarity squared. Can we cancel these? Did we not just discuss the fact that the half cells have to be separated? So we can't cancel these, can we? Unless, under what conditions can we cancel these? If the same molarity, then we can cancel. Uh-oh, ran out of room. Now then, if operate, I don't think these are the conditions stated in the notes. For the conditions stated in the notes, you can put in numbers and do the arithmetic. That's just arithmetic grinding. If operate at HO minus equals HS minus equals 1.0 throughout, Okay? Then all these are gone. These are all 1. So the only variable in this system, at least the only thing that I have not yet specified, is this. In open air. So I'm going to run this with all the solute species being present initially at a molarity of 1.0, and then I'm going to run it in open air. Back to 2045. Did you learn anything about the composition of air in 2045? What's the partial pressure of oxygen in air? 0.21 atmospheres. Any seconders for that vote? Oh, we got a few seconders. I'm seconding and I'm thirding. I'm going all the way because that's the right value. Nitrogen about 0.78 atmospheres. Oxygen 0.21. And a smattering of other gases at much smaller partial pressures. And so, if I operate this system under these conditions, is E cell bigger or smaller or same as E0 cell? Bigger, smaller, or same as E0 cell? How many votes smaller? Wonderful. Hey, now I'm dividing 1 by a number that's smaller than 1. So now I'm going to take the log of a number that's bigger than 1. That's a positive number. So now I'm going to subtract. Okay? All right? You remember when we played with the zinc copper ion system? Talked about the possibility of treating half cells with ammonia. Recognized the way to operate was to treat strictly the zinc ion half cell with ammonia to make E cell and E0 cell both go up. All right, let's take this system and consider adding six molar HCl. By using 6 molar HCl as a possible material to add to either or both half cells, can I do something to make E cell and E0 cell both increase? You looking at table 2? When you look at table 2, I want you to answer first this question. That's not the question. Is hydrogen a stronger reducer in acidic, neutral, or basic solution? Is hydrogen a stronger reducer in acidic, neutral, or basic solution? What does table 2 tell you? To answer this question, what examination are you making of the information in the table? Are you looking to see the various half reactions which contain hydrogen as a reducer, for starters? That's good. So hydrogen functioning as a reducer will mean hydrogen functioning as a reactant. Okay? So, what's the answer? Acidic, neutral, basic conditions. Under which of these conditions is hydrogen the stronger reducer? Basic, isn't it? Now let's talk about oxygen as an oxidizer. Acidic, Neutral basic conditions. Under which condition is oxygen the stronger oxidizer?
Acidic.
Which is it?
Acidic.
Acidic. Because to answer the question about oxygen behavior as an oxidizer, you have to take a look at all the half reactions which have oxygen contained within and look at them in what direction? As written or in reverse?
Reverse.
In reverse. Okay? See, if I take this table and turn every half reaction contained within and turn them around, I now have a table of oxidation potentials. The way I've written is a table of reduction potentials. Who cares? It's the same table. I once had an electrochemist tell me, I can't write these half reactions like that. These are not standard E0 values. They're only standard if you write them as oxidations. I said, you don't know what the hell you're talking about. Get out of here. I mean, I'm not bothered with people like that. I mean, this is a professional electrochemist teaching here. I don't want to listen to this stupidity. That's sheer stupidity. I just can't stand that stuff. It doesn't make any sense. All right. Now I got another question. Likely you've recognized that at home, foods kept in the refrigerator will deteriorate on standing over periods of time. Which foods deteriorate more rapidly? Acidic foods or basic foods? Well, we have an argument within the ranks of the jury here. I heard a hybrid of acidic and basic. Okay? I'll repeat the question. Which foods deteriorate more rapidly? Acidic foods or basic foods? And how many didn't vote? If you didn't vote, forget Friday, Saturday for you. Just go your way. We have just found, haven't we, regarding hydrogen consideration, that it is a stronger reducer under basic conditions? Now, what do you think leads to deterioration of food? Reaction with what? Oxygen. So if I have a basic food, is it not a stronger reducer? Will it not be more readily oxidized by oxygen because it's a stronger reducer? That's why the basic foods usually don't last as long. How about that? Now you know something about plain food chemistry. Hey, I mean, you can take spaghetti sauce. That's pretty acidic, you know, because of tomato base. That'll keep for a long time. Pickles. Pickling brine, acidic. Keep for a long time. You do that with neutral or basic foods, I mean, try to keep them for a long time. No, it won't work. They spoil pretty fast. Now we just talked about why. Okay. So what are we going to do with this? Will we add the hydrochloric acid solution to the copper hydrogen sulfide hydroxide ion half cell? To increase E0 and E cell. Will I, to accomplish the goal of making E cell and E0 cell go up, will I add the hydrochloric acid solution to the copper hydrogen sulfide ion hydroxide ion half cell? Look at table 2. We talked about this a while ago. Which is by far the more favorable conversion? Copper to copper sulfide in acidic solution or copper to copper sulfide in basic solution? Basic solution, isn't it? Electrochemical potential for the production of copper sulfide in basic solution far exceeds that for production of copper sulfide in acidic solution. The table tells you this. Remember, this is the table of thermodynamic stability information. So I want you to be able to use it. Okay? Now, what about adding the HCl solution to the oxygen-containing half cell? Did we not just wrestle with the question, how does the strength of oxygen depend on pH as an oxidizer? And what did we decide? Oxygen is better oxidizer in the presence of acid or better oxidizer in the presence of base? Look at the table. Because you want to answer the question on oxygen, you got to take every one of these oxygen-containing half reactions and look at them in a reverse direction. and at pH 0, plus 1.23 volts for the oxygen behaving as an oxidizer, right? In strongly basic solution, that decreases to 0.40 volts. That's what we're doing here. So, if I have the wherewithal to physically maintain these cells being separated from each other during operation, I'm going to purposely put the HCl solution into the oxygen-containing half cell. Because oxygen is telling me it's a much better oxidizer in the presence of acid. All right. Now then, we have reminded ourselves, when we first started to talk about the Nernst equation, that one of its principal uses is to determine K values, equilibrium constants, okay? Half cells to couple to calc. For this stuff. Now, do you recall from chapter 19 when we dealt with equilibria that involved salts of limited solubility in water? That we had to start by recognizing how KSP is defined. Remember that? Is it the material of limited solubility as reactant in equilibrium with its components, component ions? Or is it the component ions as reactants in equilibrium with the semi-soluble salt? Which way is KSP defined? The semi-soluble material is reactant or product. Which way is KSP defined? Reactant, isn't it? Okay? So tell me the reaction equation we're looking for. Let's write it down. Because if we write the correct reaction equation, we'll know what half cells to look for. There's the semi-soluble salt. What are the component ions of this stuff? The ions which react to produce this stuff. Would you bet this is one of them? Okay, you'll bet that's one of them. Clearly you should. This is a hydroxide precipitate, isn't it? What's the other ion?
Iron hexahydrate.
Iron what?
Hexahydrate.
Iron what? Hexahydrate isn't enough.
Iron 3 plus.
Iron how many plus? 3 plus? Is iron in 3 plus oxidation state in this stuff? So tell me again. Iron what? Is this it? Is that what I want to write down? How about this? Is that what I want to write down? How about that? Now let's turn this into an equation. How many of these got to react with one of these to make this stuff? 2 of them. Otherwise, I'd wind up with an ion as a product. Okay? So what I have now, is it a reaction equation? Not yet. What else? Water. Okay, water. You said water. You didn't say where water. Water. Ah, good water. Where water? Water reactant? Water product? Now tell me the half reactions to couple. And in so doing, in this coupling process, tell me which half reaction gets reversed. I'm listening. Not getting any yops.
15.
I'm not hearing very well today. I need to have that spoken more boldly and loudly.
15 and 22.
How about that? 15 and 22. Which one is reversed? 15 is reversed, so we'll put minus 15. And now we go to Nernst. E cell equals E0 cell minus 0.059 over N. What's N? I'm listening. Because you see, this is not a redox reaction. How about that? What's N? 2? Because you see in 15 and 22, you've got 2 moles of electrons transferred for each, right? Log of what term? Are we not wanting to get a K value? Specifically K for this, which is by definition KSP for this, isn't it? And under equilibrium conditions, Q and K are equal. All right? Now you know how to get this. So I ask one last question. What is this?
Minus.
What's the value for this? To solve this puzzle, right now this is an unknown. And the way you are reacting toward me, this too is an unknown. So we got one equation and 2 unknowns. We're stuck. Unless you recognize what the value for this is. What is it? Are we at equilibrium? What's the value for this? 0. How about that? We'll finish electrochem tomorrow and be into chapter 23 tomorrow. You better get at reading it. And, well, it's all right. I'll give you a reminder tomorrow about chapter 23.